Very well, so here we are on chapter 13, part 2, derivatives of trigonometric and exponential functions. So we're going to start with the derivatives of trigonometric functions. So if you see this to the left here, this is the calculator where we plug in the functions, and we have tangent and its derivative. So tangent, as you recall, is going to be these lines, and its derivative consists of these curves. But we're not going to use the definition of limit. Rather, we're going to use the fact that tangent of x is equal to sine of x over cosine of x, and find the derivative of that using the quotient rule. So remember, it's low d high minus high d low over low squared. So low would be the denominator, so cosine of x times the derivative of the numerator. That's going to be also cosine of x minus the numerator, sine of x, times the derivative of the denominator, which is minus sine of x. And all of this over cosine squared of x. So let's multiply this and see what we get. So we get cosine squared of x plus sine squared of x over cosine squared of x. And this is just 1 over cosine squared of x. This is the Pythagorean identity. And then 1 over cosine squared is secant squared of x. So that means that the derivative of tangent is secant squared. So similarly, you could also find the derivatives of cotangent, secant, and cosecant by using the quotient rule, because remember that cotangent we can write as cosine of x over sine of x, and by using the quotient rule you can find the derivative. Same thing with secant, because secant is the same as 1 over cosine of x, and cosecant is 1 over sine of x. So if you grab these three and apply the quotient rule to find the derivatives, you will find that the derivatives are these three. I'm not going to do that right now. You guys can do it as an exercise. All right, so now we're going to focus on example 13.9. So let me get rid of this. Okay, so for A, we have that y is equal to cosine of the square root of x. That means that we will have to apply the chain rule. So the derivative of this would be then derivative of the outside minus sine of square root of x times the derivative of the inside, which is the square root of x. So that would be 1/2 x to the minus 1/2. And this would end up being minus sine of the square root of x over 2 square root of x. Okay, for B, where we have that y is equal to x cubed over sine of x, let's find the derivative. We need to apply the quotient rule. So we start with the denominator. So it's going to be sine of x times 3x squared minus x cubed times the derivative of the denominator, so cosine of x, and all of this divided by sine squared of x. And I don't think we can do anything else, so that would be it. For C, we have y is equal to x squared tangent of 3x. So the derivative of this, so it's going to be x squared times the derivative of tangent, which is going to be secant squared, in this case of 3x, times 3, which would be the derivative of the inside of that tangent function, plus the second factor, tangent of 3x, times the derivative of the first factor, which would just be 2x. And then we would just have to write this down as 3x squared second squared of 3x plus 2x tangent of 3x. Okay, so now we're going to focus on D, and we'll do D over here to the left. And we have that it's y equals second squared of 3x. Very well, so notice that here we actually have to apply the chain rule and more than once, because notice that we can rewrite this as second of 3x squared. So if we want to do the derivative of this, we will have to do the chain rule, use the chain rule. So first thing is derivative of the outside. Notice that this is like saying x squared, right? So the derivative of that is 2x, or 2 times second 3x. Remember that in the chain rule we don't touch the inside until we come to the next part. So here we got to go times the derivative of second. And the derivative of second, which is right here, is second times tangent. So that times second of 3x times tangent of 3x. And this times the last derivative, which would be of 3x. So that's just times 3. Okay, but this can be simplified, right? This can be rewritten as 6 times second squared of 3x times the tangent of 3x times the tangent of 3x. And we can even rewrite this as, let's extend this a little bit. We can rewrite this as 6 times sine of 3x over cosine cubed of 3x. Okay, so here we are on example 13.10. And it says the motion of a particle moving along a straight line in the interval t between 0 and 12, t in seconds, is given by the function blah blah blah, where s is the particle's displacement in centimeters from the origin. The particle's displacement is negative when it is to the left of the origin and positive when it is to the right of the origin. A, find the exact time and displacement when the particle is furthest to the right and furthest to the left during the interval between 0 and 12. Find the particle's exact maximum velocity to the right and at what exact time it occurs. Okay, so what I'm going to do is that I'm going to focus on A and B individually. Okay, so A says find the exact time and displacement when the particle is 1 furthest to the right and 2 furthest to the left in this time interval. Okay, so let's remember that the function for displacement is this one. S of t is equal to sine of t halves minus cosine of t halves plus 1. Then to find the maximum or minimum displacement, we need the derivative of this, which is going to be the velocity function. And that is going to equal 1/2 cosine of t halves plus 1/2 sine of t halves. I'm doing the derivative of this, so I get that. Then we need to equal this to 0 to find the maximum or the minimum. So equal this to 0. Therefore, we're going to have that 1/2 sine of t halves minus 1/2 cosine of t halves. We can cancel this out in this, and then we can rewrite this as sine of t halves over cosine of t halves must be equal to -1, which is the same as saying tangent of t halves equal to -1. So remember that tangent is negative in the second and fourth quadrants. And that is when t halves is equal to 3 pi fourths or 7 pi fourths. Then we have to send this to multiply. Therefore, it's when t equals 3 pi halves or 7 pi halves. Notice that I'm not interested in other solutions because the time interval is when time is between 0, greater than 0, and less than 12. So anything greater than this will be over that time period. Okay, so that means that we have our critical points. So our critical points are going to be 3 pi halves and 7 pi halves. So what we need to do is test values that are before, between, and after these. So before 3 pi halves, we can test, for example, pi. We cannot test 0 because 0 is not included in the interval. So what happens when we plug in this into the velocity function, right? Because the velocity is going to give us the slope of the displacement. So what happens to velocity when time is pi? We do the math, we're going to get 1/2, which is positive. That means that the graph is increasing. So here, which is a maximum, I'm guessing that here it's going to start decreasing. But let's just verify using a value between 3 pi halves and 7 pi halves, something like 2 pi. So if we plug in 2 pi, what's the velocity at time 2 pi? And if we do the math, this is going to equal -1/2, which is less than 0. Therefore, the graph is decreasing. That means that 3 pi halves is a maximum. I'm assuming 7 pi halves is a minimum, but we have to test the value after that to see if the graph increases after the value 7 pi halves. So let's test 4 pi. So if we plug in 4 pi into the velocity function, we're going to get 1/2, which is greater than 0. That means that the graph is increasing, so this is a minimum. So that's all we really need. So notice that we have a maximum displacement. So maximum displacement at time equal to 3 pi halves. And when time is 3 pi halves, we need to find the displacement. So that would be s of 3 pi halves. And plugging that into the displacement function, we should get that this equals 1 plus square root of 2. So the answer would be a maximum displacement of 1 plus square root of 2 centimeters. Likewise, for the minimum, we would say that the minimum occurs at time equals 7 pi halves. So let's test, or let's see what we get when we plug in 7 pi halves into the displacement function. And if you do that, you're going to get 1 minus square root of 2. So that means that minus 1 square root of 2 centimeters at time equals 7 pi halves would be the minimum, or when it's going to be furthest to the left. And the previous one is when it's going to be furthest to the right. Very well, so here we are in part B, where they ask us to find the particle's exact maximum velocity to the right and at what exact time it occurs. Okay, so let's recall that the velocity function is 1/2 cosine of t halves plus 1/2 sine of t halves. And if we want to find the maximum or the minimum of the velocity function, we need the derivative. So the derivative of the velocity function, which is the same as the acceleration function, will be in this case equal to -1/4 sine of t halves plus 1/4 cosine of t halves. Okay, so the next thing we need to do is equal this to 0. So let's equal this to 0 and solve. So we're going to get minus 1/4 sine of t halves is equal to minus 1/4 cosine of t halves. And then we can cancel this out and this out. And we're going to say that sine of t halves over cosine of t halves is equal to 1. So we need a solution where tangent of t halves is equal to 1. So that's when tangent equals 1 and when it's positive. So remember, that's going to be here in the first quadrant and in the third quadrant. And that means that t halves has to equal pi fourths or 5 pi fourths. Then we multiply it by 2, and then t will equal either pi halves or 5 pi halves. Okay, so let's just test these values to see where we're going to get a maximum velocity and where it's going to be a minimum velocity. Right, so just plug this into the velocity function. If we plug in pi halves, if we try to test the velocity for pi halves, we're going to get square root of 2 over 2. So what happens when we plug in 5 pi halves? So 5 pi halves is going to give us negative square root of 2 over 2. So this is a positive velocity, and it's going to be the maximum velocity. And to the right, displacement we found before that was to the right in the interval between 0 and 3 pi halves. So obviously this is included. Therefore, this would be the solution. The solution would then be the maximum velocity would be square root of 2 over 2 centimeters per second at time pi halves seconds. Very well, so the next topic is derivatives of exponential functions. Let's just remember a few concepts about exponential functions. First of all, they are in the form of f of x equals b to the x, where b has to be positive, b cannot equal 1. Normally the graph passes through 0, 1 unless there's some kind of shift. Has the x-axis as a horizontal asymptote, and depending on the value of the base b, it will be continually increasing or continually decreasing or exponential decay. So the one on the left is an exponential growth, because you can see that as x increases, the function increases. And this one is exponential decay, because as x increases, the function decreases. Okay, so what is a derivative of an exponential function? First of all, we're going to look at the case where the base is Euler's number. So notice something very interesting with Euler's number or Euler's function. If you have e to the power of x, it turns out that the derivative is exactly the same line. You can see here where e to the power of x is graphed. And here in the second picture, you can see where both functions are graphed, e to the power of x and its derivative. So that just means that the slope of the tangent lines to the graph are just equal to the graph itself at all points. So then we can conclude that if f of x is e to the power of x, then the derivative is also e to the power of x. So this is with both notations, with Leibniz's and with Newton's. Now, it is important to say, though, that if you have an expression such as, for example, e to the power of x squared, then the derivative of this would be the following. It would be e to the power of x squared, which is the derivative of the outside. I'm applying the chain rule, times the derivative of the inside, which would be 2x. Okay, so here we are on example 13.11, where they ask us to differentiate each function. We're going to start with a here, and I'm going to rewrite it as y equals e to the power of 2x times e to the power of natural logarithm of x. Now the reason is that, notice there's a sum here. So in reality, we can rewrite it like this. Why do I do that? Because this expression, e to the power of natural logarithm of x, is simply x. So this can be rewritten as x times e to the power of 2x. So it would be x times the derivative of this, which is e to the power of 2x times 2, plus e to the power of 2x times the derivative of x, which is just 1. And then we can simplify this as 2x e to the 2x plus e to the 2x. So b, if you notice, we can rewrite it as, we can write b as y equals x squared plus e to the 4x, and all this to the power of 1/2. The reason is that I can see I will have to use the chain rule. So this is going to be the derivative will equal 1/2 times x squared plus e to the power of 4x to the power of minus 1/2 times, remember, the derivative of the inside. And the derivative of the inside is going to be 2x plus e to the 4x times 4. So, making this look a little bit better, we could write it as 2x plus 4 e to the power of 4x over 2 square root of x squared plus e to the 4x. And then notice we can simplify this further by factoring out 2, because we can rewrite this as 2 times x plus 2 e to the 4x over 2 square root of x squared plus e to the 4x, and we can cancel out the 2, and this would be the final expression for the derivative in case B. Okay, so now for C, let's write y is equal to e to the x minus e to the minus x over e to the x plus e to the minus x. Okay, so the derivative of this, applying the quotient rule. First we write the denominator, so e to the x plus e to the minus x times the derivative of the numerator. So that would just be e to the x plus e to the minus x minus the numerator, so e to the x minus e to the minus x times the derivative of the denominator, so e to the x minus e to the minus x. And all of this over e to the x plus e to the minus x squared. So then we can just expand the top by applying the distributive property, and we're going to get e to the power of 2x plus e to the 0, so that's 1, plus e to the 0, so that's 1 again, plus e to the power of minus 2x. And this minus, here we have to be careful with the parentheses, so I'm going to use a parenthesis for the whole expression, This is going to be e to the power of 2x, e to the power of 2x, minus e to the 0, so minus 1, minus, we're going to have e to the 0 again, so 1, and plus e to the power of minus 2x, e to the power of minus 2x, and then all of this over e to the x plus e to the minus x squared. We're going to leave this always like that. Okay, so let's see if we can simplify the expressions above. Let's start by changing the signs in the parentheses. So this will be minus, this will be plus, this will be plus, and this will be minus. And then I'm going to get rid of the other symbols just to not get confused. So this goes, this goes, this goes, and let's see if we can simplify. So notice that this and this cancel out, and then we have that this and this cancel out, and we are left with the derivative of y equaling 4 over e to the x plus e to the minus x squared. But what happens in the case where we have an exponential function in the form of y equals b to the x, where base b is a number different from Euler's number? Well, we're going to use Euler's number precisely to find the derivative of this. So notice that I could rewrite b to the x as Euler's number to the power of natural logarithm of b to the x, right? This just equals b to the x. Using the properties of logarithms, this is an exponent. Remember that with logarithms, we can send this to multiply. So I can rewrite this as e to the power of x times the natural logarithm of b. So now I can apply the chain rule to this and see what we get. So what would be the derivative of y? Well, it would be derivative of the outside. So this would stay the same, x times natural logarithm of b times the derivative of the inside. So what's the derivative of this? Well, natural logarithm of b is a number. So a number times x, that would be then simply the very coefficient of x, right? So natural logarithm of b. But notice that this is just b to the x. So we can write this as b to the x times natural logarithm of b. So this would be the derivative of b to the x. Okay, so here we are with example 13.12. Find the equation of the tangent to the curve y equals 2 to the x at the point where x equals 3. Express the equation of the line exactly in the form y equals mx plus c. So here's the word exactly. Remember, that means no decimals. Okay, so the first thing I want to find is the point of tangency because they only give me the x coordinate. So at x equals 3, y is equal to 2 to the power of 3, which is 8. So that means that the point of tangency is 3, 8, and we will need to work with this. Okay, so now let's find the slope at that point. So if the curve is y equals 2 to the x, then from what we just did, the derivative would equal 2 to the x times natural logarithm of 2. Then at x equals 3, the derivative is equal to 2 to the 3 times the natural logarithm of 2, and this is the same as 8 natural logarithm of 2, and this is the same as natural logarithm of 2 to the power of 8, which is the natural logarithm of 256. So this will be our slope. Okay, then we just have to use the point slope formula. Recall that the point slope formula says y minus y1 equals m, the slope, times x minus x1. So let's see, we have the point of tangency, and we have the slope. So we write this as y minus 8 is equal to natural logarithm of 256 times x minus 3, and then if we rearrange this, we're going to get that y is equal to natural logarithm of 256 x. Let's put this in parentheses. Plus 8 minus 3 natural logarithm of 256. All right, so here we are in example 13.13. Find the coordinates of the point P lying on the graph of y equals 5x such that the tangent to the curve at P passes through the origin. Okay, so they want us to find the coordinates of the point of tangency. But this curve, or the curve that is tangent at that point, passes through the origin. So that means that the curve that we want to find would go through 0, 0. Okay, and then let's call the coordinates of P x1, y1. x1, y1. In fact, let's call them x1, comma 5 to the x1, because that would be the y coordinate of that point P. Okay, so now let's find the derivative. So if we know that y is equal to 5 to the x, then we know that the derivative of y is 5 to the x times natural logarithm of 5. So that also means that at x equals x1, the derivative would be 5 to the x1 natural logarithm of 5. Okay, so this is the slope of that line, that tangent that passes through P and passes through the origin. So let's recall that the point slope formula is in the form y minus y1 is equal to m times x minus x1. So in this formula, this is the slope. This is the x-coordinate of the point of tangency. This is the y-coordinate of the point of tangency. So what we have here already is the slope. So let's rewrite it using the slope. So we would say that y minus y1 is equal to 5 to the x1 natural logarithm of 5 times x minus x1. Okay, so remember that what we want to find here are the coordinates x1 and y1. But we do know that this line goes through the origin. It goes through 0, 0. So that means that we could plug in 0, 0 here. And we can rewrite this as 0 minus y1 is equal to 5 to the power of x1, natural logarithm of 5 times minus x1. Okay, but let's recall that we can write y1 in terms of x, right, from here. So this is really minus 5 to the x1 is equal to, multiplying this, minus 5 to the x1 natural logarithm of 5 times x1. Therefore, notice that x1, the x-coordinate of that point of tangency, has to be 1 over natural logarithm of 5. Y is equal to 5 to the x. So to find the y-coordinate, we have to substitute x for the 1 over natural logarithm of 5. So y is equal to 5 to the power of 1 over natural logarithm of 5. We don't want really this in this form, so I want to try to solve for y here, or simplify here. So let's just use this trick here. We're going to put an exponent on both sides of the equation, and it's going to be natural logarithm of 5 and natural logarithm of 5. So notice that I'm going to get that y to the power of natural logarithm of 5 is equal to 5. So this means that y has to be equal to Euler's number. Why is that? Because Euler's number is the only one that if you have Euler's number to the power of natural logarithm of something, it equals that something. So obviously, y has to be Euler's number. Therefore, the coordinates of P must be then 1 over natural logarithm of 5, comma, E.